Good evening, friends. I'm Santosh Takale. Today's class will be taken by Prajakta Madam. Prajakta Madam, if you are available, please let me have check for your voice and presentation.
Yeah, can you hear me?
Yeah,
I will share the screen.
yeah, yeah.
Can you see?
It's
Yeah.
visible, ma'am. Please continue with class.
Yeah.
Students, thank you very much for joining in, and please follow the instructions. I'm doing some regular exercises, assignments, and using or referring the notes provided by Madam. Thank you so much. Please continue.
Okay. Yes. Okay. So in the last class, we had ended the last class on a bit hurried note. We were looking at this table, and I just said that I will repeat the portion that I covered in last 5 minutes again, and then start from there. So I will just go ahead and remove this portion. Yeah. Um, So basically, we were looking at we looked at the formulae for displacement, velocity, and acceleration by considering SHM as a projection of UCM, and we also saw. I mentioned also that these formulae are essentially equivalent to the formula that we had derived earlier in the second class. So they're not like different formulae; they are just derived using a different method, which gives a more physical picture of SHM. And from these three forms, so these were the three formulas that we derived, and from these three formulae, we then went on to find out what is the value of theta, what is the value of x, v, and acceleration at different timestamps. So I had mentioned, if you guys remember, I had mentioned that suppose this is some particle that is performing a linear SHM, and these are the boundaries. This is minus a, and this is a, and this is the mean position. I had mentioned how the time period is divided between these two positions. Like what is the amount of time that it requires for particle to go from mean position to here and then come back to the mean position, go to the negative extreme and then come back here. So all of these four segments essentially take um, t is time period. So they all take 1/4 of time period. So they take equal amount of time. And based on that we write this table in terms of like what is the value of displacement at time 0, what is the value at time t by 4. So t by 4 is essentially one segment covered, so it will go from mean to extreme or from extreme to mean, like that. And I think this table was essentially it's just you have to plug in the values of say small t, or you have to plug in the values of, yeah, you have to plug in the values of small t and then find out these values for extreme cases. We'll just do the plotting of these values. So I had mentioned in the last class, for example, ki the phase difference between displacement and displacement and velocity is pi by 2 radian, and the phase difference between velocity and acceleration is pi by 2 radian. So we'll just plot these things and see key plots, like how the plots look essentially. What do you mean by pi by 2 phase difference? We'll just see that in the and start today's class on that note. So so this is the time axis, or it could also be omega t axis, which is theta. So time and theta are always equivalent. They map one on one to each other because time, like omega t, is just theta. So these two things map onto each other. So the x-axis could either be t or it could also be omega t, which is theta. So that is not an issue. And we'll plot displacement here. So let's just say the maximum value of displacement we see is a, and the minimum value is minus a. So we'll just say this is a and this is minus a. And then now we'll just divide, we'll just say that this is the whole time period t. So this will be t by 2, this will be t by 4, and this will be 3t by 4. And we'll just plot these values. So at time 0, we get displacement to be 0. So this is here. Then at time t by 4, we have the value of a. So it will be here. Then again it comes down to 0. Then it goes to minus a, and it again goes to 0. So we'll just connect these points, and we'll get a nice sine plot. So this is a sine omega t, right? This is displacement. Then we'll go ahead and do the same thing for velocity, and again we'll map the same locations, t by 4, t by 2, 3t by 4, and t. This time again it's t, and this time the y-axis is velocity. And we see कि velocity का maximum value is a omega, and the minimum value is minus a omega. At t is equal to 0, we have the maximum value, so it will be here. Then at t by 2, t by 4, we have 0. Then at t by 2, uh, we have minus a omega, then again 0, and then plus omega. This is the whole cycle. And then, so this is essentially a cos graph, right? So this is not a, I mean, this is a sine graph. You know the sine graph. And then if you happen to start at 1, then it will become a cos graph. Bad drawing, but yeah. And this is the cos graph, which is a omega cos omega t, which is velocity. So what that means is कि अगर आपने ये जो origin है, ये जो x axis है, वो 0 से मतलब यहाँ से start होता है. But if we shift this x axis to here, which is so t by 4 is pi by 2, right? And if we plot this x axis here, then this is essentially what we get after this is essentially the cos graph, which means that there's a difference of pi by 2 between the sine graph and cos graph, and essentially same difference between displacement graph and velocity graph. And similarly, if we go ahead and plot the acceleration, so the maximum value of acceleration is a omega square, and minimum value is minus a omega square, and then same 4 points. What we'll get is we start from we again here start from 0, and then we go to minus a omega square, then again 0, then again a omega square and 0. तो ये जो ग्राफ अगर आप कंपेयर करोगे तो दैट इज शिफ्टेड बाय पाई radians. It is shifted, it is origin here, and then it goes into negative first, not into positive first. So that is a difference of pi radian between displacement and velocity. So same thing, ki phase difference of pi radian between displacement and acceleration. Sorry, displacement and acceleration, not between displacement and velocity. So these are the same plots that we made now. So this was the case if your particle is starting from the mean position. And now they have also given the case for particles starting in the uh, extreme position, so positive extreme position. And we know that if the particle is starting from extreme position, the particle starts from extreme position, we know that the phi is pi by 2. The phase difference is pi by 2, and so that essentially gives displacement of a cos omega t. Instead of a sin omega t, we get a cos omega t. And now there's a very easy way of calculating velocity and acceleration if you know the x. So you don't have to go all the way around like how we found out velocity in last class. You can just take derivatives, because we know that velocity is essentially first time derivative of displacement. So that will just come out to be equal to a omega sine omega t and minus sine. And acceleration is again just second derivative of displacement or first derivative of velocity, which will come out to be minus a omega square cos omega t, right? And this is how you can calculate velocity and acceleration directly if you know the displacement. So this is again the same values. Ki we know ki x ka value is a cos omega t. So taking the derivative, we get velocity to be minus a omega sin omega t, and we get the acceleration of minus a omega square cos omega t. And again, this is a similar table that we saw for the first case. It's just similar. I mean, it's again the same thing, that you have to just plug in the values of time and find out the extreme cases for acceleration, velocity, and displacement. And you can do it the same way. And these plots are also plotted in the same way. What you can essentially just take note of is now everything has been shifted with a pi by 2 phase difference again. So here the plot is of sine, like displacement is sine function, whereas here the displacement is cos function. Then again, this is a sine function and this is a cos function again, but the negative cos function. So everything has been, so the plots for mean position have been just shifted by pi by 2 to get the plots for extreme position. This is something you can just remember very easily. Um, yeah, and I mean that's pretty much it from this section. So we'll move on to the next section, which is, I mean, it is a quite interesting section, the next section, and you also get a lot of exam questions, like competitive exam questions on this part. So that the next part is essentially composition of two SHMs having same period along the same path. What that means is you take some particle performing SHM like usual. It is going between, say, um, okay, let's not say what are the extreme positions. We'll just say it is doing performing some SHM. On top of that, you give another force that essentially is giving another SHM to the same particle. So here is now this particle which is performing two SHMs simultaneously. You can also, like, the correct term to use would be superposition of two SHMs. So one SHM on top of another SHM. And what is the condition for these SHMs? So the condition is it has same period and along the same path. So period is omega, so, or like t. So the time period or angular frequency is the same of both the SHMs, and the particle is going around the same path. Like, it's not that ki ek particle, I mean, ek SHM is making the particle move in one path and the another SHM. I mean, that is not possible because it's one particle, so it has to move along the same path, regardless of how many SHMs are acting on it. So that is the condition. The condition is essentially that you have to have SHM with similar period. Now, what can change? I'll just write this down. So we need to have same omega slash t. What can change is the amplitude. Amplitudes can change, and the um. Okay, what else can change? Wait. Yeah, phase. Phase can change. Phase difference can change. Amplitudes can change, and the phases of, or like phase difference values of the SHM can change. And in this situation, we can find out what is the total free, what is the total motion looks like. I mean, you add two SHMs on a particular particle. Is the resultant motion also an SHM, or does it perform some other kind of random motion? And if it is an SHM, then what are the amplitudes and the phase factors for the resultant SHM essentially? So that is what we are going to find out. कि अगर एक particle पे दो और दो से ज़्यादा, it can also be two or more, दो से ज़्यादा SHMs are acting on a single particle with same omega or same t, then what is the resultant motion? I mean, what does it look like? So that is the part that we'll cover here. And we can now just consider two SHMs, which we can write as x1 is equal to a1 sine omega t plus plus phi 1. So A1 is the amplitude of first SHM, and second, and the phi 1 is the phase difference in first SHM. And x2 we can write as A2 sine omega t plus phi 2. You have to take note that these omegas are same. I mean, the formulae that we are going to derive, they only apply if your frequency is same for both of the SHMs. Otherwise, you'll have to find a more complicated equation to denote the resultant motion. Um, so we'll just find total displacement, which can just be given as x1 plus x2, which is then a1 sine omega t plus phi plus a2 sine omega t plus phi 2. Now you probably know this formula already, which is that sine a plus b is equal to sine a cos b plus cos A sin B. So this is a trigonometric identity, and we can just put this, like use this identity to open this sin omega t plus phi, and then sin omega t plus phi 2. And using that, we can write this as x total is equal to a1 sin omega t cos phi 1 plus cos omega t sin phi 1. And then similarly for second term, sin omega t cos phi 2 plus cos omega t sin phi 2. Now we know that a1, a2, phi 1 and phi 2, these all are constants. Their values are not changing. We set their values and they stay constant during the motion, whereas the changing value is, I mean, the variable here is t essentially. So the term with variable is sin omega t. So we can just take sin omega t common and rearrange this equation as xt is equal to, we can just take sin omega t and then we'll write a1 cos phi 1. So this term is gone, plus a2 cos phi 2. This term is gone. And then we'll take cos omega t, a1 sin phi 1. This term is gone. And a2 sin phi 2. So we have just rearranged the terms into, and we have separated the variable part and the constant part. Right now in the bracket we have the two constant parts, and we can just give a different name to the constant, because I mean constant case are whatever you can do, and it will only give you another constant. So we can just use another simplified letter. Instead of writing these all four terms, we can just write a um, simple um, one variable for all these terms, and you can just say ki we'll assume r1 is equal to a1 cos phi 1 plus a2 cos phi 2, and r2 will assume that it is equal to a1 sin phi 1 plus a2 sin phi 2. And now because both of these terms in the R1 are cos terms, we can also just assume that there is some vector R and its cos component is basically this vector. So the component of R is R1, which is equal to this whole term. And we can just write this entire term as R cos some angle delta. So we'll just assume these are all constant numbers, and we can do this. And similarly, because in this equation all terms are sine, we can just write this as the sine component of R. And now the xt equation will look like sine omega t r cos delta plus cos omega t r sine delta. And if we look again, we can use the sine cos sine formula. Sine cos sine, and r is just constant, so we can pull r outside and we can write this as sine omega t plus delta, which is here. So we have reached here. Right now, if we look at this equation, we quickly realize that this is also a motion, also an equation of simple harmonic motion, because we have been writing x is equal to a sine omega t so far, right? So this is exactly the same equation with just a replaced with r. So what that essentially means is, doing all this mathematical jugglery, we get um, r, which is the amplitude of this resultant SHM. So the resultant motion of this whole exercise, I mean this whole system, is also SHM. It is also SHM with same period, and uh, so the amplitude of this motion will be given by r, and r is defined using these two components. So r1 and r2 are essentially components of r, sine component and cos component, and using, I mean, this is again of SHM. So the resultant motion now we know is SHM, and now we can find out, we can go ahead and find out r. And also delta is now the phase difference in the resultant SHM. So I'll just write this down. Resultant motion is also SHM with amplitude is equal to R, and phase difference is equal to delta. And now what we'll do is we'll find the values of R and delta in terms of original A1, A2, phi 1 and phi 2, because we don't know, I mean, we don't know R and delta ka like a formula or like an equation form, and that we need this in terms of original factors which are known to us, they are given to us, the A1, A2 and phi 1, phi 2. So we'll find R and delta. So so now, as I said, R is a vector with R cos theta, R cos delta, and R cos, R sine delta as their component. So in if you have any vector with two given components, we know how to find the magnitude of that vector, right? So the magnitude of R is going to be basically R. I mean, it's basically going to be root of squares of r1 square plus r2 square. And I mean, if this is just going to be equal to r square cos square delta plus r square sine square delta, and now cos square delta plus sine square delta is just going to be 1, and so this is going to be root of r square, which is r. I mean, that is what we want to find out, right? So we are just going to use this formula, but instead of doing this cos square plus sine square one thing, we are now going to substitute these values. So we have r cos delta ka value and r sine delta ka value in terms of a1, a2, phi 1, phi 2, and we are just going to substitute that here. So we are going to write r square is equal to a1 cos phi 1 plus a2 cos phi 2 square. This is r cos delta square, and now r sine delta square is a1 sine phi 1 plus a2 sine phi 2, and then uska square. And now we'll just open these brackets, and it is like slightly tedious algebra, but I'll do it. And I mean, all the terms are going to just cancel out, and we are going to left with very few terms. So I mean, it's fine. So this is just going to be a plus b bracket square formula, which is a1 square cos square phi 1 plus a2 square cos square phi 2 plus 2a1 a2 cos phi 1 um, cos phi 2. This is first bracket. And then second bracket will be a1 square sine square theta 1 plus a2 square sine square, oh no, phi 2, sorry, phi 1 phi 2 plus 2a1 a2 cos, no, no, not cos, what am I doing? Sine phi 1 sine phi 2. So we'll just open these brackets, and now you can easily see what is going to happen is cos square phi 1 plus sine square phi 1 is going to be 1, and we are then just going to be left with a1 square. Same thing here, and we will be left with a2 square. And now we have this thing which is 2a1 a2 uh, into cos phi 1, no, cos phi 1 cos phi 2 plus sine phi 1 sine phi 2. And now this is again another trigonometric formula like the one I wrote here. And this trigonometric formula, so cos A cos B plus sine A sine B is just equal to cos A minus B, and A minus B in this case is just going to be phi 1 minus phi 2. Okay. And so this is r square is just going to be a1 square plus a2 square, plus 2a1 a2 cos phi 1 sine phi 2 plus 2a1 a2 cos phi 2 square. And now this is r square is just going to be a1 square plus a2 square plus 2a1 a2 cos phi 1 sine phi 2 plus 2a1 a2 cos phi 2 square. And so this is r square is just going to be a1 square plus a2 square plus 2a1 a2 cos of phi 1 minus phi 2. And that implies ki, I'll just do it here. That will imply ki r is just equal to root of a1 square plus a2 square, this whole thing essentially. And this is the value of equivalent amplitude, or the amplitude of the resultant motion because of because of superposition of two SHMs. And now similarly you can also find delta. To find delta, we again have these two things which are r cos theta, r cos delta and r sin delta in this term. And now we want to find out delta. We can just easily say ki cos delta is equal to this whole term divided by r, right? But let's just say we don't know r, and I mean, is it like it'll become then two-step process. For example, in some question, you have been only asked to find this delta, and you're not asked to find r. If you are asked to find r and delta, then you can just find r using the formula that you just derived, and then put this r here, and you'll easily get delta, right? Because you just have to take then cos inverse of this whole term divided by r. Let's say in some question you're only asked delta, then you don't need to calculate r before finding delta, because that's just a two-step process. So instead of doing that, we are just going to eliminate this r so that we don't have to find the value of r. And the easiest way of eliminating the r using these two equations is just taking tan delta. So if we take sine delta divided by cos delta, the r will get cancelled, and what we are going to be left with is just division of these two things. So I'll just write here r sine delta divided by r cos delta is just going to r going to get cancelled. This is just to eliminate r. If you already know the amplitude of resultant motion, then you don't even need to use this formula. You can just use one of the r sine or delta, r cos delta, one of those formulae. But if you don't want to find the r and add an extra step to your calculation, then this is an easy formula to just eliminate the r value. And this is just going to be tan delta, which is equal to a1 sine phi 1 plus a2 sine phi 2 divided by a1 cos phi 1 plus a2 cos phi 2. And this is just to give the value of phase difference of the resultant motion. I mean, yeah, this is pretty much it from this example, and we are also taking special cases, uh, essentially extreme cases, where for example one case is going to be two SHMs are in phase, which means that phi 1 minus phi 2 is going to be 0. And if you now look here, phi 1 minus phi 2 is 0, and cos 0 we know is 1. So this formula is just going to be r is equal to a1 square plus a2 square plus 2a1 a2 into 1. So this cos term is going to go away. And then more special case of this will be to take a1 is equal to a2, which just means that here this will be a1 square plus again a1 square plus 2a1 into a1, which is again 2a1 square. So this is just going to be 4a1 square, and uska root is going to be 2a1. So this is given here, r is equal to 2a or like 2a1, whatever is the equal amplitude of the two SHMs. And then another special case is given to be SHMs are at 90 degree, which is out of phase. And in that case, so no, SHMs are 90 degree out of phase, which means that the phase difference between the two SHMs is 90 degree. So essentially phi 1 minus phi 2 is 90 degree, and cos of 90 degree is 0. So this entire term will just go away. It will just become 0. And what will be left with is only this root of a1 square plus a2 square, right? And in that case, agar your a1 is equal to a2, then this is just going to be 2a1 square. So root of 2a1 square, and the root of 2a1 square is going to just be 2a1, or like just 2a. Oh, sorry, root 2a. And this is what is given here. the r is just going to be root of 2a. And then the next case is 180 degrees out of phase, which means that one particle, one SHM starts from this extreme, like this positive extreme it starts and then goes here. And then another SHM is just starting from this negative SHM, negative extreme and going in this direction. And you can imagine in this case what physically will happen. So, for example, um, okay, so you are like holding a string between this is you and say this is your friend, and you are holding the string from one side and this another friend is holding the string from another side, and say you move the string in such a way that it will cover the first, it will go to positive amplitude first, and your friend makes it like oscillate in such a way that this string will cover the negative oscillation first. And eventually what you guys are going to achieve is a plain string which is not performing any motion. So it's just going to stay still because your motion, the way you are oscillating the string, is just going to cancel the way your friend is going to oscillate the string. So this is exactly what happens here. Uh, they also have to be at equal amplitude. So, or in opposite phases and equal amplitude. But to look at this more mathematically, what we'll get here is cos theta minus theta, phi 1 minus phi 2 is going to be 180 because they are 180 degrees out of phase. And this is just minus 1. So the thing that we are going to get is a1 square plus a2 square minus a1 a2. So this is the formula for a general case. But in this, if we plug a1 is equal to a2 is equal to a, then we will just get a square plus a square minus uh, minus 2. Sorry, here this should be 2 minus 2a square, and this is just going to be plus 2a square minus 2a square, which is just going to be 0. So the amplitude of motion is going to turn out 0 if if the if the two SHMs are completely out of phase and equal amplitude. And this you can also imagine in a physical example, or like in a physical sense you can imagine how this happens. Okay. And um, so we can take one example based on this thing so that you can understand how to apply these formulae. And there is I found one nice example in the below exercises, like the exercises below your chapter. So I will just take that example so that you will also understand that this kind of question can also come in your board exam because it is given below the chapter. And I'm just going to take this question and we will solve this quickly. Yeah. Um, so the question is two parallel SHMs represented by x1 is equal to 5 sine 4 pi t plus pi by 3, and x2 is equal to 3 sine 4 pi by t plus pi by 4. This is a slightly like calculation based question. So because the answer, as you can see already, it is in decimals and the angle is also like very weird. So we'll use calculator, and my guess is you are allowed to use calculators in your board exams. In the competitive exams, I don't think you guys have access to calculators, but in that case, they will give um, calculations or like angles which the values you know already. So they won't give like 54 degrees and 23 arcs. They won't give questions like this. So in board exams, they can give, but you have access to calculator, so that is okay. Now we'll just write the given exam, like given values quickly. So we have here a1 is equal to 5 meter, then a2, sorry, this is centimeter, not meter. So a1 is equal to 5 centimeter, a2 is equal to 3 centimeter. Phi 1 they have given is pi by 3 radian, and phi 2 is pi by 4 radian. And they have asked determine the amplitude and epoch of resultant SHM. So we have like ready-made formula. These examples are actually very easy if you understand the exact question and you don't mess up the numbers essentially, but yeah, we'll see that. So now we can just compare these two equations. I mean, I think you guys already got how I have reached, I mean, how I found these. Like a1 a2 is clear and phi1 phi2 is clear, and here you can just compare this with omega t and you'll get the value of omega to be 4 pi. It's not asked here, but like in some example that might be the question. So that's how you can just compare the equations and find out the values of variables. And we now have a direct formula. So r is just going to be root of a1 square plus a2 square plus 2 a1 a2 cos of phi 1 minus phi 2. So this is just going to be a1 square is 25 plus 9 plus 5 threes are 15 and then 30 into cos of phi 1 minus phi 2. So pi by 3 is just 60 and pi by 4 is 45. So this subtraction is going to be 15 degrees. And I'll just open calculator and quickly find out what is 15, like cos of 15 degrees. So this is 0.9659 and I can just, I mean, multiply the things here itself. Into 30 is this value and plus 25 plus 9 is going to be 34. So we have this as 62 plus 97. So, and I'm just going to also take root here itself. I mean, it'll be around something around 8, but yeah, just to find out the exact value. So this is going to be 7.9358. And this is again going to be in centimeter because they have given the values in centimeter. And so you can see the answer is 7.936, which is just like they have taken 3 significant digits, and that is fine. And again, now to find delta, we again have formula which is tan inverse of um, a1 sine phi 1. So a1 is 5 into sine phi 1 sine 60 essentially is root 3 by 2 plus a2 is 3 into sine of 45, which is 1 by root 2 divided by 5 into cos of 60, which is 1 by 2, and 3 into again 1 by root 2 because 45 ka sine and cos are same. I can just calculate this entire thing on calculator. That is also fine. But I'm just going to, for the sake of simplification, I'm just going to multiply everything. Basically, I'm just going to make everything in with denominator 2. So I'm just going to multiply this with root 2 and then just divide and multiply this by root 2. And then this will become 5 root 3 divided plus 3 root 2 divided by 2 and then divided by 5 plus 3 root 2 divided by 2. You can simplify this however you like, or you can just directly do it on calculator. And this 2 and 2 is just going to cancel and we are going to get tan inverse of 5 root 3 plus 3 root 2 divided by 5 plus 3 root 2. And I'll probably not do this in, I mean, here you can try doing this calculation at home and you'll get some value of tan inverse and then you can take tan inverse on calculator itself just to confirm that you actually get this angle. So this is like a very easy category of questions. You just have to compare the equations, given equations of two SHM with the formula for displacement, and then find out A1, A2, A2, and then just put these values in these two equations. That is like the simplest kind of questions they can ask in the exams. So now moving forward, I just wanted to like show you what kind of questions based on this can be asked, and I have also put some questions based on this in the example problems that like the sheet that I'll send you. And now I'll move on to the next part, which is a very like important part. They are very like this in this section. There are again only very small two formulae, but they have very important physical meaning, as well as they are important in terms of exams, because you will get a lot of questions on this next section, which is the energy of particle in SHM. Now we already know that there are like two kinds of energy. First is kinetic energy, and second is potential energy. And we know that the total energy is just going to be equal to kinetic energy plus potential energy. And the same thing is true also here. I mean, it is true for everything. So we are going to separately first find the kinetic energy. We'll just denote this using EK, and then we will find the potential energy, which is EP. I mean, the derivation for kinetic energy is pretty simple. We know that in general, any system has kinetic energy, which is equal to half mv square. And we have also derived the formula for V. So V, we remember, is omega root of a square minus x square, or it is also, you can also write it in form of a omega cos omega t plus pi, right? These both are a formulae for V, and you can just, I mean, it is the easiest thing. You have to just substitute this here, and then you'll get half m omega square a square minus x square, or the same thing is going to be just equal to m a square omega square cos square omega t plus 5. And now, if you remember, we had written k is equal to m omega square, and you can also substitute that just to reduce one term, and then ek is going to be half k a square minus x square, which is also equal to half k. So this is m and this is omega square. A square cos square omega t plus 5. And I mean, this is the easiest derivation for kinetic energy. Just like one step, you just have to use half mv square formula, and this is again very important equation. You have to remember this ek is equal to half k a square minus x square. I mean, this is the formula that is most often used, but this can also be asked at some point. So this is essentially you can use when you know the x, right? And you can use this formula when you know the t value. So, I mean, yeah, that is just for the convenience sake. And then second is going to be EP, which is value for potential energy. For that, we will basically look at a system which is again performing SHM, and let's say it is at some position X. And when it is at some position X, we stretch it a little bit further by dx extension, and then we calculate the force that it requires to move this particle from x to x plus dx, and then that infinitesimal force is just going to be minus k dx. And wait, I will just I mean, I'll just highlight so that you can get the, I mean, I have already highlighted, but yeah. uh, huh. So this force is going to be minus k dx, and now we want to, because see, potential energy is basically ability to, I mean, the energy that is stored that can potentially do work. And so we will first find out what is the work that gets done when you move the block by certain small amount, and then integrating that work done, we will essentially find the stored potential energy. Okay, so that is the idea here. And so we have the force now, and we know that small infinitesimal energy, I mean energy in general, can be given by f ds or dx, whatever, and there will be minus sign because it is a restoring energy. And so we will just substitute this we'll just substitute this f here. No, wait, this is a slight mistake. Okay, I'll just start from beginning. This won't be Huh. Okay, so just erase whatever I said because I made a slight mistake, and now we'll start again. But again, the same case, we have to consider a particle at some point x performing SHM. At point x, the restoring force that is going to act on that particle is just going to be minus kx because it is at point x. And now we are going to do work. So the work is essentially, it will take the particle from this x position to some infinitesimal change of x plus dx position. So the change, I mean the work that we are performing is to move the particle by small amount dx from x to x plus dx, right? So that is that is where the work is getting performed. And we know that whenever we want to calculate work done by some force, we just write that as minus f dx, which is the small infinitesimal amount of work that is performed. Okay, and minus sign is here because it is a restoring force, or it is a stored energy that is applied to do that restoring, applied to do that work, because it is against the force. It is not in the direction of force, but it is against the force. I hope like this is clear. And now the small infinitesimal extension is dx, and we'll just substitute the value of f here, which is which is going to be minus kx dx, and this work is just going to be kx dx. Now this is a small amount of work for small amount of displacement. If we integrate this whole thing, we are just going to get the whole um, the like entire amount of work essentially to perform the whole motion from whatever the whole one cycle. And that is just going to be d omega, which is integration of kx dx. And if you remember the formula that I had written in the first class for integration, so it's just going to be kx square divided by 2 plus c, but we can always omit the c and put the c to be at the center of the system, at the zero essentially. And this is going to be the work that that the force will do in the entire cycle or in the entire one oscillation. And this is, where is this work coming from? That is coming from the potential energy stored in the system. And so that way we are going to find this same, I mean, we are going to this is essentially the case that the potential energy stored in the system which does the entire work is half kx square. And this is going to be another important formula in this section, which is the formula for potential energy. So we have the kinetic energy and we have the potential energy. These are very small formulae. And also again, you can write the same thing as half k a square sine square omega t plus phi. You can just write x as a sine omega t plus phi, and that is also entirely fine. And again, the same thing will happen if you know the displacement, then you can use this formula. If you know the time, then you can use this formula. So that is again the same thing. Um, and I'm going to just highlight it here, which is k square, and then you can also write k as m omega square. You can do all sorts of combinations and just use whatever is convenient given in your question essentially. And this is k omega square sine square omega t plus y. And here they have given, like they have just like I didn't understand. I think this is a typo. This should not be cos square. This should just be sine square. Um, like my guess is this is a typo in the book. You can also probably ask your teachers. But I just thought of pointing it out so that you don't get confused. Um, and no. Huh. Now we have E kinetic energy equal to half k. Wait, I forgot. Huh. K a square minus x square, or which is also equal to half k a square cos square omega t plus phi, and the potential energy is half k x square is equal to half k a square sine square omega t plus theta. And then your total energy is just going to be sum of these two, which is just going to be half k a square minus half k x square plus half k x square, which is just going to be half k a square. And you can also look at here. So cos square omega t plus phi and sin square omega t plus phi is just going to be 1. And you're going to be left with half k a square. So the total energy is just going to be half ka square, which means that this is independent of the position or time. So the total energy throughout the motion in the system, like if you see here, it is dependent on x, and this is also dependent on x, and they're both dependent on time. So the kinetic energy and potential energy of the system is going to change with respect to the position or time in the system, but the total energy of the system will always be conserved. So it is always going to be half k square, ka square, which is independent of time or independent of position. So this quantity is going to stay same, and it is going to be conserved during the whole motion. And at so that essentially means कि जहाँ पे potential energy कम होगी वहाँ पे kinetic energy ज़्यादा होगी, and जहाँ पे kinetic energy ज़्यादा होगी वहाँ पे potential energy कम होगी, because this total, the sum has to be always the same. So the total energy is conserved, but kinetic energy and potential energy keep changing, and they keep interconverting into each other. So I think this is enough for this class, and we'll look at some questions now, and we will cover the next portion. So we have reached till here, I think, and we will look at the next section in the next class. I will just open the questions. Yeah. So I have again updated the notes with the formulae that we learned today, and I've also put these trigonometric relations so that if you have not covered those in your class so far, then you'll just get like a background of which formulae I am using. And I put the equations for these things. I've also added the solutions for questions that I had given as homework in the last class. I hope at least some of you are doing these questions. I mean, they are pretty easy questions, and just wanted to show that there are also easy questions that are asked in these kinds of exams. So you don't have to like feel very worried that what kind of questions like they ask. There are also easy questions, and you just have to look out for them. And if you try out these questions by yourself, I'm pretty sure that you'll be able to solve them by yourself as well. And I've given solutions, so you can just go through that and check whatever your solutions are and if they match or not. I have also added a few more problems, again, 5 more problems after today's class. So, first 3 problems are based on what we had. No, actually, any three, like 3 of these problems are based on earlier classes, and 2 problems I have given based on what we learned today, like the superposition equations. So you can also try to solve these. This is just to give you an idea of how to apply the formulae that we derived in form of questions. कि you might not always understand कि हाँ हमने ये formula derive किया, पर then अगर question आता है तो हम apply कैसे करेंगे वो formula question में. तो these questions are just to give you flavor कि हमने class में ये formula derive किया आज, and then these are some sample questions based on that. So that knowledge is still fresh in your mind, and you can directly apply, and then you can understand कि हाँ ऐसे questions आ सकते हैं. And I have not added any new questions because I had already put 2 questions that we had said we'll solve in the next class. So we'll just solve those questions. This one is pretty simple, like a conceptual question, which is they just ask you the phase difference between displacement and acceleration of a particle in simple harmonic motion. And we have directly seen the answer to this question. The answer should be pi rad. So Displacement and velocity is pi by 2. Velocity and acceleration is again pi by 2. And displacement and acceleration is pi, right? So the answer is that only. So this was a direct question. And then another question I had added many classes ago was based on energy. So we will solve this question quickly. Um, they are basically asking कि a particle starts from mean position. So particle starts from mean position. That means we can write x as a sine omega t. If particle starts from extreme position, this same formula will be a cos omega t. And performs SHM with a period of 4 seconds. So t is going to be 4 seconds. They ask at what times kinetic energy is 50% of the total energy. So we saw today itself the kinetic energy. I will just use the same notation. Kinetic energy is equal to half k a square minus x square, and the total energy is equal to half k a square. तो उन्होंने पूछा क्या है बेसिकली क्वेश्चन में कि the kinetic energy is 50% of total energy. So we'll just write E K is 50% of ET, which means half K A square minus x square is equal to 1 by 2 of half K square. So this 1 by 2 will cancel here, and then we can just open the brackets and write K square minus Kx square is equal to half K square. And then we can just find out kx square, which is equal to k square minus half k square is just half k square, and k ko k cancel ho jayega, and then we will have x square is equal to half a square, which means that x is equal to a by root 2. ठीक है, तो एक्स एक्स मिल गया हमें कि जहाँ पे ये कंडीशन सेटिस्फाई हो रही है. तो उन्होंने पूछा है कि at what time. So they have asked us time, and we have found out the x value. So we can just use the formula that we wrote here. X is equal to a sine omega t, and then that will give us x is equal to a sine omega t. We can just substitute x ka value as a upon root 2. Then again a sine omega. They have given the value of t, and we know that t is equal to 2 pi by omega. So omega is equal to 2 pi by t, and this is just going to be 2 pi upon um, t is 4. So 2 pi upon 4 sin omega t, and we have to find the small t. And इसको ये cancel हो जाएगा, and then we will have sin pi t by 2 is equal to 1 upon root 2, and we know that sin pi by 4 is equal to 1 by root 2, right? So this value is just going to be pi by 4. So pi t by 2 is equal to pi by 4, and then this will just be pi cancel, and this will just be t is equal to 1 by 2, which is equal to 0.5 seconds. And the answer is going to be 0.5 seconds. Yeah, correct. So so this is how you can solve the questions based on kinetic energy thing. And that is pretty much it for this class. There are some examples that I have given you for homework, and I hope you're doing them. Like before the next class, you can do them, and then I'll put up the solutions. So you can check your solutions with them. I'll stop today's class now.
Okay, madam. Thank you so much. Okay.
Yeah.
So we will meet again on the next Monday. You are planning to have 1.5 hours class. We'll check the it's mostly possible, but there is some commitment from my end. So I'll check and I'll update you by phone. Okay.
Yeah, sure. That works.
Good night, madam.
Yeah,
And thank
thank
you very
you.
much, students, for joining in. Bye bye. Good night.